Okay, so in chapter 2, we started talking about forces. We started talking about finding resultants, and we got into rectangular components. So we're going to pick up and talk about force systems, and then we're going to look at moments, and then ultimately we'll look at non-concurrent force systems. So that'll finish this out. So let me get to the point I want to get into. Like I said, if you guys have any questions, let me know. Let's see. All right, so this is where we want to pick up right here. So when we are looking at, when you're looking at statics problems, and actually we haven't gotten into the exact component of statics yet, but just in vectors in general, you have to determine what type of force system you have. And the first thing you need to understand is whether it's what we call coplanar or non-coplanar. So for coplanar forces, what you're saying is that all forces will lie in your same two-dimensional plane. And so this is a very simplistic form of what's going on. Most structures really are not going to be a two-dimensional kind of flat thing. So coplanar is not really the reality, but we model things very often that much just that way, just to simplify things. So in this course, you're going to be strictly dealing with two-dimensional coplanar force systems. So that just simplifies it. If we get to the non-coplanar, what you're saying is not all your forces lie in the same plane, three-dimensional. And what that gets into is multiple equations. So you will see with the coplanar, you're basically dealing with 3 equations, rather. When we get into non-coplanar, it would be 6 sets of equations. Okay, so we're not going to be doing anything from a non-coplanar standpoint. So that's the good news. So the next thing we look at is the types of force systems that we would encounter to be able to solve a resultant. So you have a couple of different kinds that we talk about. The first one we've already talked about a little bit last week was the concurrent force system. So if you recall, when we talk about concurrent force systems, what we're saying is that all the forces lines of action intersect at one unique point. Okay, so if you have 2 vectors or 10 vectors, it doesn't matter. They all have to intersect at the same point to be truly concurrent. And we've already kind of looked at some of those examples, but we'll look at some more today. Then we get into what's called a parallel force system, and what we're saying is that none of the forces actually intersect in this type of force system. So when you get into this type of force system, you have to solve it a particular way. So we can't use the techniques that we've already used with the concurrent force system. So a lot of different types of things will be modeled as parallel force systems, as we'll see, and we'll get into that a little bit later today. And then probably the hardest type to deal with is the non-concurrent. So what you have in this case is that some of the forces are going to intersect, but some of them aren't. So that's a truly non-concurrent. So the parallel force system is a specialized case of the non-concurrent, but it's a little bit simpler because everything is truly parallel. So in that case, nothing intersects, okay? So we have the concurrent, parallel, and the non-concurrent. And it really, again, that's the easiest to solve, probably second easiest to solve, and that's the hardest. And one of the things you have to do when you get into these problems is truly determine what's going on. And that way you'll know how to apply things. Okay, so let's start out and look at the concurrent force system. So as we said, this is a force system in which all of your forces intersect at one specific point. Now, you have to look at your picture because sometimes it may not look like they're intersecting, but you have to follow their lines of action back to a specific point, okay? And in this case, you can't have any parallel forces within it, okay? So anything that would be not concurrent with the rest of them throws it into a different types of system. So this also uses what's called a three-force principle, which basically states that if you have non-parallel forces that act on a body, the lines have to intersect to be concurrent, or for what we call equilibrium. And if you have one of those forces that is not concurrent, then you throw it into you're going to get what's called rotation. And once you have rotation going on, as we'll talk about today, you've gotten out of a concurrent force system. So let's take a look at the, we'll go through these first and we'll take a look at some examples. So for the parallel force system, what we're saying again is that all of your forces involved are truly parallel to each other. And again, this is just a way of modeling things. I mean, that's not going to be totally true, but an example of a structure that you might model this way would be like a floor slab. So your concrete floor slab might have just forces coming down on it, like columns or pieces of furniture. So those things we would pretty much model just parallel, because gravity is going to essentially be parallel in that room. So that would be an example of a parallel force system. So in this, we say that none of their forces or lines of action are going to intersect ever. And in this case, we're going to have to use what's called rotational equilibrium to solve this. So rotational equilibrium is actually a very simple process, and you're going to find parallel force systems are going to be one of the easiest types to solve. Even, I think, sometimes easier than the concurrent force systems. So the last class or case that we're going to look at is the non-concurrent force system. And again, what we're saying here is that not all of your lines of action intersect at a single unique point. So you may have two of them that intersect, and then two that are parallel, or two that are completely intersected at a different location. So in this case, you're going to have to do some things to get to that point, and you may have to use rotational equilibrium to solve this. So this is saying you don't always use a rotational equilibrium, but you may have to. Whereas in the parallel force system, we're going to also always use that rotational equilibrium. And I'll tell you this, with this type, usually rotational equilibrium is one that you will definitely need to use. So it kind of works the same way. All right, so let's start to consider some things. So once you've determined what type of force system you have, then you can determine how you're going to solve it. Okay, so the first thing you have to do, determine if it's coplanar or non-coplanar, and we already said everything's going to be coplanar. So the next step is to say, okay, is it a non-concurrent, is it concurrent, is it a parallel? Once we know that, then it takes us down the path of resolution. So if you can't identify the force system, you're going to have a tough time applying anything, okay? So that's going to take some time to understand this as you get into these problems, because that'll be really important as we get into this further on, okay? So we're going to look at finding the resultant of concurrent force systems, and you have four methods. We've already talked about this last week. You basically have four methods to do this. One is the triangle law. We have the polygon method, which we know is a really sloppy, messy method. A lot of mistakes can happen. Component method, which is probably going to be your best method. And then a graphical solution, which is said if you have a scale and a protractor or even AutoCAD, that's a great tool. So we're going to look at a real simple example, and I'm going to solve it both ways. I'm going to solve it with a triangle law, and then we're going to come back and do it with components just to contrast them. They're basically the same in that sense, but sometimes you'll see that one method is going to be easier than the other. So let me flip over here to my whiteboard. Let me give me a sec here. All right, let's go to taskbar. So we're going to assume that we have a car that is sitting on an icy surface. So in other words, it's going to be frictionless. So once we get this thing moving, we're going to be able to just move it in the direction that we want. So I'm just going to represent my car here. by a simple rectangle. And we're going to say a couple things about this, that we're going to have one vector coming from the front of it. Give me a sec to draw this. So we're going to have one vector at about a 45-degree angle. So I'm going to go ahead and draw this up, going in this direction. And we're going to have another vector at a pretty acute angle with respect to that, going kind of like this. So these are chains that we're going to attach to this, and we're going to have one that we're pulling in this direction and one that we're pulling in this direction. And we're going to have a 45-degree angle here and a 25-degree angle here with respect to the front of that car. We're going to want this thing to travel completely, let's say up like that, or in that vertical direction. So that's going to be a pure vertical direction. So that's going to represent our resultant. We're going to have a chain here and a chain here. This chain will be 100 pounds, and this chain we don't know. So what we're going to want to solve is the amount of pull in this chain here when we're pulling at 100 here at 45 and keeping this at 25. So once we get this thing going, it's going to go straight. So we're going to neglect the weight of the car, and we're going to say it's a frictionless surface. So what we're going to do is come over, and I'm going to solve this with triangle tip-to-tail method. So what I'm going to do is come over here, and I'm going to start out, going to redraw this. So I'm going to come over here. We're going to give this a vector doing like this. This represents my 45-degree vector. I'm going to attach to that. Give me a sec here. Okay, so what we have now, there's our triangle. Let me label the parts here. So this guy represents our 100-pound vector. This guy represents our unknown. We'll just call this vector B. So this is B. We don't know that. And this vector is actually the resultant, because we know that it's going to go in a straight direction, but we also don't know its weight. Okay, so everybody see how that works? And if we have a truly horizontal line here, then this angle also has to be at 45. Now also knowing if we have that parallel, that horizontal line here, we know that this is 25 and this is 45. So when we add those two together, that would give me an angle of 70 degrees in here. And since this is 45, that has to be 45, because we know that that's straight up. That's the direction that the car is going to go. Does everybody follow me so far? Okay. So if we add these two together and subtract that from 180, we can get an angle here, which gives us 65 degrees. So we have an angle, we have a triangle. It's not a right triangle, but how can we solve this if we want to know what the magnitude of vector B is, or even the magnitude of the resultant? How could we solve that? We have a triangle, right? We have a side and an angle, and we have angles all inside. So what would we use to solve that? Any suggestions? Okay, well, what we have is a sine law, and I can say that the sine of 65 is to 100 as the sine of 45 is to B. And I'm going to write that slightly differently. I'm going to say that B is to the sine of the side it's opposite which is 45, as 100, the magnitude of that chain is to the side, the angle that it's opposite, which is 65. So you can see that we can solve B very readily if we take the sine of 45 times 100, and we're going to divide that by the sine of 65. What we come up with is, when we do this, is we get the value, basically 78 pounds. So what this is saying now is that if you get this thing going on a frictionless surface, if we pull this at 120 or 100 pounds at 45 degrees, and this with a magnitude of 78 pounds at 25 degrees, this is going to go straight. Okay. So that's using a triangle method. Now, you could also do this by breaking these guys down into components and resolving it that way. So I can take the, well, let's just do it. We're going to go ahead and do that real quick. So let me erase this. So another way, an alternate way to do that is to break this vector down. So we could have an x component. So we can have an x component for this vector. Oops. We'll get out of there. All right, so we have an x component. Sorry about that. Not cooperating with me. All right, so we have an x component for this vector. We'll call that vector A. And that's going to be 100 times the cosine of 45. But we also know that this is going to be going in a negative x direction. So that would turn out to be a negative value. And once we do that, we'll find that that's going to be 70.71. The y component is going to be the same, actually, because sine and cosine are the same for 45, except it's going to give us a positive 70.71. So as we look at this, what we should know is that for this thing to go straight, if this x component is at 70.71, B's x component also has to be at 70.71 because they have to cancel. So what we can say is this has to be equal to x of B, but it has to be opposite sign in order for it to cancel. Okay. So what you would have is, if we drew a vector there, let me draw this, pull this down here. So we have one vector like this. One vector like this. And one vector like this. So this represents B's vector. This is B. What we know is this horizontal component is 70.71. And again, we're saying, because we know that the resultant of this guy has to go straight, in order for that to happen, these guys have to be the same in the x, but they have to cancel. That's why I was able to write that. And I know that this is 25 degrees. So by using a cosine relationship, I know that the cosine of 25 is going to be equal to 70.71 over B. Solving B gives us 70.71 divided by the cosine of 25 and we'll get the same number when we do that math. There's that. So there's two methods. You can either use triangle law, components. It just depends on what the situation is. And a lot of times, I will tell you that your component methods are probably going to be the better of the solutions to use. Okay? So let me go ahead and I'll minimize this and we'll go back. Is everybody okay so far?
Can you go back just for a quick second?
Absolutely.
All good.
Okay, absolutely. Let's go back, Max. Hold on a sec. Yeah. Okay. What's up?
So we're giving her headshots.
Okay, we're all good now.
You're good?
Yeah.
Okay. So here's the thing that you had to do here. Hold on a minute, guys. I'm sorry. Well, I'm in the middle of a lecture. What's up? No, it's okay. Okay, all right. Okay, I'm sorry. Any questions then? You're okay?
All good.
Okay, so the real thing that's really important here that you got to understand is, and I guess I should have written this a little bit different. What I really should have said is that x of A plus x of B has to equal 0 for this to work, okay? And so by doing that, if this is a negative, when you bring this over, it becomes a positive kind of thing, okay? That's why this became positive. So you have to think about that. And the only reason that worked is because this was truly, the resultant was going in that direction, okay? So we're going to see some problems as we get into that, how that'll work, okay? All right, we're good then? We can go back?
Yeah.
Okay, I'm going to go ahead. I'm going to create a new one here because I'm going to go back and let's go back to PowerPoint. All right, so that was using both the triangle law and the component method, and you wouldn't necessarily need to do both, obviously. You just do the one that works the best for you, okay? All right, so we need to talk about movement because even in statics, we don't talk about movement, but we use it as a tool to kind of solve things. So there's potentially two types of movement that a body could undergo when you're dealing with statics. We can talk about the tendency of the body to move translationally, which means it moves in a straight line under an influence of forces. So what that means is it truly doesn't have any rotation. And then your other kind you have is a rotational movement where the body is about some kind of fixed point, and that's going to tend to cause a rotational force, which we call a moment. So again, if we go over and we look here real quick, let me go back to this guy. You guys are very used to rotational and translational because in AutoCAD you kind of use that concept. So what we're saying is, if you have, let me just draw something real quick. If you have a body right here and you're pushing on this with a force, okay, and if it's truly rotational movement, when this thing moves in that direction, what's going to happen is this guy will have the same orientation. So in other words, if this is straight up and you're pushing it with this force in that direction, it's going to stay straight up, okay? That's an example of translation. When you use the move command in AutoCAD, that's exactly how something works in AutoCAD. If you pick it up and you move it, if it's at 30 degrees here, it'll be 30 degrees over here, okay? That's what we call translation. Has everybody got that idea? Okay, I will assume that's yes. All right, so if we have true rotation, what rotation says is that if we have a body and it's pinned, okay, so in other words, we have it pinned somehow, like say maybe right there, and we put a force on this guy, let's see, right here, because it's pinned, that body's going to kind of want to spin like that, okay? And this is an example of rotational movement. And the further you get from the point of pinning, the more rotation. So you can think of, there's a distance, a separation here, like right there, that distance from here to here, that distance times this force will give you the amount of rotation, which we define as a moment. So we say that the distance, if this is D, and this is your force F, you can say that your moment is going to be equal to your distance times your force. Notice force is going to stay pretty constant, so as distance gets further away, the moment will increase, and if distance gets closer to that point, then the moment will disappear. As a matter of fact, if D goes to 0, this will go to 0, okay? So if we bring the force right through that point of pinning, then you have no rotation, which should make sense, okay? And you're going to use this technique, moment, a lot when you get into these problems. And moments will have a particular unit associated with them. If your distance is in feet and your force is in pounds, we would call this moment a foot-pound, or some people call it a pound-foot. If you were in kilonewtons and meters, it would be a kilonewton meter, okay? So those are going to be important. Typical units, we said, are going to be foot-pound, inch-pound, kip-pound, or I'm sorry, kip-inch, those kind of things, okay? So keep that in mind, because this is the one place where units is kind of critical. We said last week that units aren't as involved, but they do get a little bit more involved when we get into that, okay? So let's go back here. Let me see, minimize this. Okay, so that's rotational. So the magnitude of the rotational force, as we just said, is very dependent on the two items, the magnitude of the force and that perpendicular distance. And I forgot to mention that distance is perpendicular to the direction or the action line. So let me go back here real quick. So this distance is perpendicular to that right there. Okay, so you're always talking about that perpendicular distance to your line of action. Okay, and that can be the tough part sometimes when we get into this. As we'll see, I'm going to show you some examples of how we have to solve that if you get into those issues. Okay, so from an equation standpoint, again, we talk about this concept of moment. Moment is equal to your force times your distance. And remember, that distance is the perpendicular distance to the force's line of action. And typical units, inch-pound, foot-pound, inch-kip if you're imperial, newton-meter, kilonewton-meter if you're dealing with metric types problems, okay? So we'll talk about this other thing, which we call the principle of moments. Let me back out here. I'm going to go back over. We're going to solve a moment problem real quick, and then we're going to ramp it up a little bit. So moments are going to be pretty important as you get into the rest of statics. And so this is a good place. We need to really pick up on this. So let me start a new thing here. Okay. Does anybody have any questions so far? Are we okay on this?
All good.
Okay. All right. So I'm going to draw a little bracket, if you will, and we're going to put some dimensions on it. We're going to put some forces on it, so you can kind of see to illustrate this. And then I'm gonna ramp it up a little bit and show you how you can make this a little bit more complex, the way it can work for you. So let's see, we're gonna have this bracket like this. Okay, so what we have is a bracket, and this bracket has a weight on it. We're gonna say at the end of this bracket, it's got 100 kip weight. And this arm of this bracket is 4 feet, and the height of this bracket is 6 feet, okay? So when you take moments, a couple of things. You always take moments from a selected point. So I could talk about taking a moment here, which we could call it point A. I could take a moment here, which we could call that B, or I could take a moment here, which we could call C. And we're going to do all three of those just to show you how this works. We're going to assume that this is 90 degrees and this is 90 degrees, so everything's nice and parallel. So this distance is perpendicular to this line of action, okay? So this is my force line of action. That 4 feet would be perpendicular to that. So if we wanted to solve the moment of this situation at point A, basically you're just going to say that the moment about point A is going to be equal to the force, which is 100 kips, times the distance perpendicularly measured, which happens to be 4. And so that gives us, or yields for us, 400 kip feet. Okay? Does everybody see that? That's pretty simple, right? Okay, so moment at B, if we took the moment at B, what do we find with that? Well, again, it's a force times a distance. In this case, it's a force times this distance, which is also happens to be 400 kip feet. So what we're finding, if we look at this, that any point along this line, whether you took moments anywhere here or here, you're going to get the same moment value. Okay, does everybody see that?
Okay.
So there's another thing I didn't talk about is notice that your force is going down. So moments have an implied direction to them, okay? Either clockwise or counterclockwise. So truly, you can see if I'm sitting at A, it would be tending to spin this guy clockwise, or yeah, clockwise, and same thing at B. So a lot of people are going to define clockwise as positive and counterclockwise as negative. It truly doesn't matter what you use, okay, as long as you're consistent. So you have to be consistent throughout a problem. So if you say moments are always clockwise and they're positive, then you just have to roll with that always. So if I assume that clockwise moments are positive, then I would say that this is a positive 400 in both cases, okay? So that's also important to know, okay? So if we looked at C, the moment at C is going to be a force. What is the distance at point C to that line of action? Well, if we look at this, the line of action is actually coming through point C. So what that means is the distance is 0. So the moment at point C is actually turns out to be 0 kip feet. Okay? Everybody seen how that works? Any questions?
Okay. Yeah, can you explain that again?
Sure. Which part?
With C, like
Okay.
how those all.
Because if I'm taking moments right at C, notice that the line of action of the force is coming through C. So there is no distance.
Okay.
Okay, now let's do this, okay? Let's come over to the middle of this arm right here. What would that distance from C to that point be? We'll call this D. What would that
Just-
distance be if I'm at the midpoint?
At the midpoint,
Yeah.
2 feet?
Yeah, it'd be 2. So in this case, notice that the moment at D is going to be 100 times 2, which is going to give me 200.
Oh, I see.
Okay, you see what's happening?
Yeah.
So the further I get this way, the more the moment increases.
Okay.
As I approach the line of action, it goes to 0. But then if I would get on this side of the line of action, I'm going to start to have a negative moment if I'm defining clockwise positive. Does that make sense?
Yeah.
Okay. So this is a really, really important concept. It's actually pretty simple. I mean, you just got to remember that the distance has to be measured perpendicular to the line of action. And if the line of action comes through the moment point, it drops out. It goes to 0, which is going to be a really good thing for you guys to understand later on, because you're going to be able to utilize that to get rid of stuff. Okay. We want to simplify every time we can. Okay. Is everybody okay with that? Okay, so we're going to take a look at where moments can get really messy. Okay, so let me clean this up a little bit here. I'm going to replace some things here. Let me get rid of that. Get rid of that. Get rid of that. And get rid of this. So what's going to happen? Let's change this up a little bit. Select that. So if I happen to delete, well, not delete, but change the angle. Okay, I'm going to change the angle of my force. So let's say we got a force acting like this now. Nope. And it's going to be 30 degrees with respect to that vertical. So we'll use the same 100 kip force. This problem becomes a lot messier, okay? Because what I have to know is what is the perpendicular distance from A to that line of action, okay? So this becomes a lot messier. So let's take a look at solving that. So if I do truly have that situation, what I'm saying is I really need to know what is the distance from here to here, okay? I don't know what that distance is, but I can solve it using a little bit of trig. Let's kind of look at that real quick. So I'm going to draw myself a couple of triangles here. So what I can do through some trig is if I know, if I drop this guy down, I know this distance is 4 feet. I can solve this distance. My thing is not to scale, just kind of recognize that. And also recognize the fact that this is 90-degree angle here, because I have to know this distance. So I don't know this distance. So if I want to solve this moment with this force about that point, I have to know the perpendicular distance. Does everybody see what I'm getting at? Yes? This problem is a lot messier, okay? So if we know that this right here is 4 feet, we can solve this, and ultimately we can solve that. Does anybody know how we would solve this if we know that this is 6 feet and that's 30 degrees? We're just going to call this X right here. which is the distance from here to here. If we look at this, we have a tangent relationship here, okay? So we can say that the tangent of 30 is equal to opposite over adjacent. Solving for x, that gets me 6 times the tan of 30 degrees. Okay, so by doing that, we get, we should come up with 3.46. You can check the math on that. Let me just check that real quick. .46. So by knowing this is 346 and we add that to that, what we'll get is this total distance on this triangle here from here to here is 4.46. So I added the 4 plus the 346. Now, the problem is I still need this, okay? So I do know if this is 30, this is also 30 degrees. So what you have is a hypotenuse and a side adjacent to that. So you can use a cosine relationship. So I can say that this distance, we'll just call that d. So what we'll have is the cosine of 30 is going to be equal to distance d, that's this distance here, over 7.46. D turns out to be 7.46 times the cosine of 30. And ultimately that gives me a distance of 6.46. Now, the thing is, I had to do all of that just to get this distance, and I haven't even solved the moment yet, but now I can solve it pretty easily because moment is just simply equal to a force times a distance. So we have 100 kips times that distance perpendicularly measured through point A of 6.46, which gets us 646, and this would be kip feet. And if I'm assuming that positive or clockwise moments are positive, I would call this a positive 646, okay? So, extremely messy, right? All of this work, all of this geometrics right here was just to get this number, okay? So you can see the moment was very simple. Is everybody okay with that? You get bogged down in the geometry maybe, but did everybody understand what I did there?
Yeah.
Okay, it's a mess though, right? You agree? Real mess? Not simple. So there's an easier way, and here's what we can do. Instead of having to solve this distance, we can use this property called the principle of moments. The principle of moments is going to allow you to take those forces and break them down. And what it basically says is that a moment created by a force about a point is going to be exactly equal to that same moment created by components of that force about a point. So if we can break that force down into components in X and Y, we can apply those moments and add them, and we'll get the same result, and it's going to be a lot simpler than all that stuff that I had to do before. The other principle that you can use sometimes is that principle of transmissibility, which says that a force can be assumed to act anywhere along its line of action, and it has the same effect on that body, okay? Has the same effect on that body. So I'm going to show you how to use the principle of moments, and we'll get that same answer that we just did really a lot simpler. Okay, so let's go back over. Now again, if you don't understand something, let me know, okay? All right, so I'm going to use this same diagram. Let me clean it up a little bit, but I'm not going to need any of this. Watch what will happen as we get into this. Okay, so let me get rid of all this junk and this junk as well. Give me a sec here to clean this up. So basically what we're going to do is take this vector and replace it with its components. So we're going to use the rectangular component concept is what we're going to get into. Okay. All right. So instead of solving this distance, what this method says is I can take and solve this vector and this vector. So I can replace this vector with its horizontal component and its vertical component, and I can get that same answer a lot simpler. So let's see, we're going to take this guy, and notice this 30 degrees, that's 30, not 36. This 30 degrees is the vertical component, and this is the horizontal, so we have to think about that, okay? So what I'm going to do is I'm going to come here, and I'm going to say that my y component, because I can see that pretty easily, y is going to be equal to 100 times the cosine of 30 degrees. Okay, and let's see what we get there. Okay, so that gives me 86.6, and that would be in terms of kips. So the x component in this case is going to be a sine relationship because it's actually coming over here. So if we take the sine of 30 rather, times 100, that gives me 50 kips. Okay, so all I simply did was took this vector and I'm going to break him down into his two components. So what I'm going to do is I'm going to get rid of this vector and I'm going to use the replacements for that. So I can make this easier. So we've got one vector now acting down and one vector acting out like that. So I have this vector, that's my y component, okay? And I've got this vector, which is acting that way, okay? So all I did was took that 100 kip vector at 30 degrees and I broke him down into components. Okay, is everybody okay with that? Okay. So to apply principle of moments, then you're just going to take a moment at A, and we're going to define clockwise moments as positive. And we're going to say, if I look at this vector right here, this is going to be tending to turn this guy clockwise. Now I'm not looking at this guy yet, just this one. With respect to A, it's tending to turn that bracket positively. So I'm going to say that's a positive moment at the force. times its distance, which is 4 feet, because this is 4 feet measured to that, okay? And then I have another moment, 50, and that's also tending to turn that bracket clockwise, 50 times his distance, which is 6. So when you take 86.6 times 4 plus 50 times 6, what you come up with is the exact same number we just calculated. And that would be in kip feet. So this is applying the principle of moments, and this is the one you want to use the most, because if you have to solve that perpendicular distance to the vector, sometimes that's impossible. And sometimes it's so hard, it's just crazy to try to do it. If I can break a vector down, I can apply principle of moments. Does everybody see how that works? That's really important when we get into moments. You're going to have plenty of problems to work on for Thursday, but is there anything I can talk about before we move on? No questions?
None that I can think of.
I'm sorry, did you say you were good?
Yeah.
Okay. All right, so if you're not grasping it yet, it's going to take you a little bit, but you'll see once you get into it, it's not that big of a deal. There is a couple things you got to think about, though, with these directions. You got to look at which way this guy's tending to turn that bracket with respect to A, so it would make a difference. Can anybody tell me what would happen if we took a moment up here? How would this change? Would we get the same number? Nobody has a suggestion? Well, this point up here, if we took a moment up here, we would still have 4 times 86, but this one would drop out of the equation because there's no distance here. So the moment at this point would just be 86 times 4, okay? So it does make a difference when you have more than one vector going through that you're dealing with. All right? Okay, I'm going to go back. So we did not have to use transmissibility here, but just keep in mind that transmissibility is going to be an important principle, particularly when we get to non-concurrence, okay? But we did apply this thing called the principle of moments, which said that a moment created by a force about a point is exactly the same as the moment that is created by the components of that force about the point. And this is a way of simplifying your moment problem, okay? So you're going to want to use that one. All right. So that was the end of that section. So I'm going to go into the next section, which we're going to start to talk about parallel force systems. Okay, so let me go ahead and close this. Okay, so we've talked about concurrent force systems. And remember, with concurrent force systems, you basically have triangle law, method of components, polygon method, or graphical. When you get to parallel force systems, you're going to have to use a whole different process. Now, it does rely on moments. So moments become really critical. And it's not that hard because the forces are all parallel. So the nice thing is that you don't really have to calculate distance as much. So we're going to look at the resultants of the parallel force system. And the parallel force system is, as I said, particularly useful when you model certain things. One would be what you think of as a beam. So beams typically, like beams of a truss or beams of a bridge or something like that, we kind of model those loads to be parallel. And again, that's not totally true, but it's just a simplification. So the resultant of a parallel force system is just a vector, essentially, that is going to have the same effect on the body as the original system. Okay, so that's the parallel system that it's replacing. And with this, you must meet two criteria to have a proper solution. You have to satisfy translational characteristic and rotational. So, in other words, the translational movement and the rotational movement in the original system and the replacement system, they must be equal for this to work. Okay? So here's what we're saying from a graphical standpoint. If this up here represents your beam, and you're loading it with a force and a distance over, and another force and a distance over, and another force and a distance over, you can replace those three vectors with one vector, the resultant, but you have to know where to replace it, where to put it rather. So is it here, or is it here, or is it here? And what determines that distance x is this rotation that's happening right here has to be equal to the rotation that's happening here. So essentially it's pretty simple. You just take the forces and add those together, and that gets you R. And then you're going to take this moment plus this moment plus this moment, and essentially you're going to be able to get this X in some way. Okay. So the parallel force system is really actually pretty easy to use, but graphically again, you're going to take this guy, you're going to replace these three vectors with one vector, but you have to put it in the right spot. And notice I have a point A notated here. So you always have to work off of the same point. So whatever these distances are with relationship to A, this distance will also be with relationship to A. But theoretically, I can take a moment anywhere I want on this beam, so I could take it on the right side, or I could take it in the middle. Okay, so if I take it in the middle here, I have to take it in the middle here. Okay? So to satisfy translational is really simple. It's just simply defined as the sum of the forces. So force 1 plus 2 plus 3 up to the ith force. So however many forces you have, you just sum them. But you do have to recognize the fact that forces going up, forces going down would have different signs. So you have to apply an algebraic sign to it. Okay? So we're just the resultant, just summing them. And most people by default define forces acting up as positive and forces acting down as negative. Again, you can do it any way you want to as long as you're consistent. What we're going to do and what the book does, if a force is up, it's positive. If it's down, it's negative. Okay? So we're going to be consistent with that throughout, and that's what the book always uses. Okay? So the resultant has to act at a location that's going to produce the same movement rotationally, or the actual, what we would call the moment. So the moment that is produced in the original system is going to be equal to the moment in the replacement system. It has to be if you have a true resultant. So what you're going to do is first define rotational. Rotational is saying this, is that the moment due to force 1 and its distance plus the moment due to force 2 and its distance plus the moment, which is force 3 and its distance, has to be equal to the resultant times this distance. Okay. And again, the algebraic sign of this side has to be equal to the algebraic sign on this side. So if this moment totally here is a positive, then this moment has to be positive. And again, that's negative. That also has to be negative. So we're going to also typically define clockwise as positive and counterclockwise as negative. All right. Once you have solved this top equation, what you'll know R and you'll know this, but you won't know X. to solve x, what you're going to do is just divide this value of moment through by your r value, and you'll know where your location is. So we're going to take a look at an example problem utilizing this. Okay, so let me go over here. Do a new drawing here. So we're going to say that we have a simply supported beam of some kind. Give me a sec to draw it here. I'm going to have a beam that's kind of like here, and what I'm going to do is put a couple of forces on this guy. So we're going to have, let's see, we'll put a force at the end of this beam, put a force at the other end. We're going to place a force here. We're going to place a force here. Okay, so we have 4 forces to consider. Let me go ahead and I'm going to put their directions. So this guy's acting down, this guy's acting down, this guy's acting down, and this guy's going to be acting up. So this is going to be a 2 kip load. This is going to be a 6 kip load. This is going to be a 5 kip load. And this is going to be a 3 kip load. So we know that this is 5 feet. We're going to say that this is 5 feet from force to force, and then that this is 4 feet. Okay, so we have 5 from there to there, 5 from there to there, and 4 from there to there. Okay, so we want to get rid of all of these vectors and replace them with one vector that's uniquely can be placed on that, and we have to know what its force is going to be, and we have to know what its location is going to be. So I've got to do 2 things I want to think about here. One is I need to know where I'm taking moments. So I'm going to just define my moments at the end of the beam. We're going to call that point A. The other thing is I'm going to say forces acting up and rotation are positive. Okay, so forces acting up are positive. Rotations acting clockwise are positive. Okay? So in this type of problem, the first thing you're going to do is solve your resultant, R. So R is just simply taking and summing these forces. So I have -2 plus -6 plus -5 plus 3. Okay. And again, the negative sign is coming from the fact that I'm saying acting down is negative and acting up is positive. So we're just utilizing that, and what we get is, looks like a -10. So that tells me that the force is going down. Okay, is everybody with me on that? And that would be unit is kips. So that's pretty simple. There's nothing to that. All right. So now we need to know, now that we know that we're going to replace these guys with one unique force going down at 10 kips, what we need to do now is determine, okay, so where would we place that with respect to A? Well, the other thing that we have is that we know that the moment of this system and the moment of this has to equal. So what I'm going to do is solve the moment of this guy first, and then we're going to come back and apply that. So I'm going to say that the moment at point A on the original system is going to just be equal to each individual moment. So for this one, it's acting down, but it's causing a positive rotation, but there is no distance. So this one just disappears. So this one is going to be 5 times 6, and it's tending to turn it clockwise. So that is going to be a plus 6 kips times 5. Now, is anybody wondering why this is positive and not negative? Because that force is negative? Is anybody thinking that right now?
Yeah.
Okay, here's the reason, and you've got to think about this. The direction of a moment is completely counter. It has nothing to do with the direction of the force, okay? Even though we know this force is acting down, so from a force standpoint, we're saying it's negative, but what kind of rotation, if you put your finger right here and let this thing spin, which way would that tend to spin this? It would tend to spin it what? In a clockwise direction. And we're saying clockwise is positive. So this is indicating the direction of the spin, not the direction of the force. So it has nothing to do with, well, I mean, it's related to it, but you can't say just because your force is negative, your moment is negative, okay? You have to separate those two things out. That's going to be probably the hardest thing for some of you guys to do at first, okay? So just remember that this is guiding what's happening here, okay? Does that help?
That makes sense.
All right. Now, again, that's gonna take you some time, trust me. So you're gonna have to deal with that a little bit, and eventually, you're gonna get it wrong sometimes, but let's see what happens on this one. If we look at this 3 kip load, we know that we define it as positive because we're saying it's acting up. But if we look at the moment of this, we know that this is tending to spin this beam in a counterclockwise direction. So we're going to say that moment is going to be a negative moment times the force of the distance 10, okay? So we're getting a 0 moment here, we're getting a positive moment here, and we're getting a negative moment here. Is that making sense?
Where did you get the 10?
The 10 is the distance from A to the vector. 5 feet plus 5 feet.
Okay.
That's your perpendicular distance, okay? So on beam problems like this, it's really straightforward. Usually you're just measuring left or right, okay? It's not as involved as like what we just got into with that bracket, okay? We don't have to think quite as much here. The thing that you really got to look at, though, is your direction of spin or your direction of moment, okay? That's important, very important, okay? Is that making, we okay now?
Yep.
Okay, so the last moment is going to be a 5 kip moment times this distance. So it's going to be 5 plus 5 plus 4. So we're 14 feet over. And that moment would tend to be positive because it's taking that beam in a clockwise direction. So we're going to say direction of the moment is going to be 5 or plus 5 times 14. So when we do this math, this is going to give us the result. So let's look at this. This is moment, drops out. This is your next moment. That's your direction. That's your force. That's your distance. Direction, force, distance, direction, force, distance. So when we solve this, let's see what we come up with. We got 6 times 5. 3 times 10. Plus 5 times 14. Whoa. What are we getting there? Anybody get an answer?
That's 70.
70 plus or minus?
Plus.
Okay. So what that tells me is it has to be a clockwise moment. Okay. And what would the unit of that be? Kip feet. Or you could call it feet kip. Some people will reverse that. Okay. So this moment on this beam currently, if you're taking moments a day, is going to have a 70 kip foot moment. So here's what you're going to say now. R times X has to equal to the moment at A, okay? Moment of the replacement system has to be equal to the moment of the original system, okay? So we know what R is. R is 10 times X times 70. Now, again, this is saying that it's down, but that isn't negative, because if this is a positive moment, this has to be a positive moment, okay? You can't change the signs. But by solving this, what are we going to get for X? What do we get for X? Simply what?
7.
7 feet. So what this says is you could get rid of all of these guys right here, and you're going to replace them. You're going to come over 7 feet, and you would put your 10 kip vector acting down, and that would have the same exact effect on this beam as the original system did, okay? So it's a two-step process. You solve your resultant first, and then you solve your moment and just equate it. And what you're doing is taking what you have for your resultant and dividing it by your moment, or your moment by that, excuse me. Okay. Also remember, if this is a positive moment, this also has to be a positive moment. So there's no way that this could be negative 10 just because that guy's down. So if you think about it, if I put that vector over here going down, it's definitely going to be wanting to spin that beam. Okay. We seen how that works? Parallel force systems are going to be the easiest thing that you do. They're even easier than concurrence. Once you understand signs with your moments, that's probably going to be the biggest deal. It's getting your signs right at first, okay? But that will get easier, and you're going to have we're going to have problems that we're going to be solving. We'll spend a lot of time with this on Thursday. But I do have some problems in the book that I want you to do, okay? All right, so if there's no questions, I'm going to go back and we're going to tackle the last topic we're going to get into today, which is non-concurrence. So these tend to be the harder of the process, okay? But it kind of uses everything we just talked about here. So that's the good news. So let's go back here. So non-concurrence, what you've got going on is where we said it's not just true parallel, it's not concurrent, it's kind of maybe a mixture. But what you have is not everything is going to come through at the same point. And so really, if you think about structures and that kind of stuff, a lot of structures are going to be of the non-concurrent type when you really get into it. So the forces don't all intersect at a common point. That's your big key deal with this. So there's steps that you have to deal with. And here's the thing, normally when we solve a resultant, we just need to know its magnitude and its direction. But when we do a non-concurrent, we're going to need to know not only the magnitude and the direction, but we're going to have to be able to solve the point or the line of application. And this right here turns out to be the hard part. Usually solving the magnitude and the direction, that's not that big of a deal, okay? So this is pretty straightforward, but this is the point where really that makes you think a little bit. So there's going to be, I'm going to go through a problem with you, show you the steps, and then you'll have homework problems to do. And again, Thursday, that's probably a big part of what we're going to be getting into. But let's take a look at the steps that we go through when we do this, okay? So when you have a non-concurrent force system and you want to solve the resultant, you can basically use these 6 steps. You don't always have to use them because sometimes things are already broken down. But the first thing you want to do is any forces that are not truly horizontal or truly vertical rather, you want to break them down into their rectangular components. So if everything is already horizontal or vertical, you're done with step 1. You don't need to worry about it, okay? Once you have it broken down into vertical forces and horizontal forces, you're going to sum your vertical component forces, you're going to sum your horizontal components, and then you'll be able to solve the magnitude using the Pythagorean theorem. After you do that, then you'll be able to solve the direction of that vector using the arctangent relationship. So we've already done this step. This is actually just a component method. It's all we're doing here. Component method where you're breaking it down, summing verticals, summing horizontals, solving the magnitude, and solving the direction. So the step 6 is going to be the hard part. To get the actual point or line of application, you're going to have to use moments to find its location. And the other thing very often you're going to have to use is the principle of transmissibility. Okay, so we're going to utilize both moments and transmissibility to solve 6. Okay, so I'm going to we're going to work a little example here, show you how this works. And if I go fast or too fast, just let me know, stop me. So we're going to do a non-concurrent right now. Let me go back to my whiteboard here. Let me just clean this up. So we're going to assume we have another type of bracket with some loads on it. So give me a sec here to draw it. So I'm going to have a bracket with a vector. There's the bracket arm, and then there's a vector coming off of it. I'll draw that here in a minute. So let me get this drawn. Okay, so there's my bracket. So I'm going to load that with a couple of forces. I'm going to have one force going like this. So he's right parallel with that vector. There's going to be another force coming about right in the middle of this thing, like this. And we're going to have another force like at about a 45-degree angle, something like that. Okay, so there's our situation. So let me draw the directions and label this. So we know that this vector is acting down. This is a 200-pound vector. This vector is acting this way. We're going to say he's 50 pounds. And this vector is acting like this at 100. And we're going to say that horizontal, give me a sec here. That the horizontal, that's a 45-degree angle. Okay, so we know that this side of that bracket is 3 feet up, and this is 4 feet from the edge and 4 feet over. Okay, we're also going to take moments at this point. Now, a lot of times in these problems, they're going to tell you where to take moments, and sometimes you won't be told that. So if you have a choice, you can take a moment where it's convenient for you. But for this case, we're going to reference it to point A. Okay, does everybody understand what we got? A simple little bracket. It's 3 feet this way, 8 feet this way, 200-pound force in the middle, 50-pound force. We're going to assume that force is running parallel with Y. This force is parallel with X. And this force is 45 degrees with respect to either the X or the Y. Okay. So the first thing I want to do is get rid of any vectors that are not parallel to X or Y. So what I want to do is break this vector down into his X and Y components. Okay. So what I'm going to do is I'm going to take X is going to be 100 times the cosine of 45. And the nice thing about that is because it's a 45-degree angle, you guys should know that The cosine and the sine are the same. So what we come up with in x, we're also going to have in y. So let's see, what does that give us? Sine. The cosine of 45 is 707. And that gives us 70.71. The y is going to be actually equal to the same thing. We're going to also get 70.71. Okay, so that's our very first step. So what I'm going to do is I'm going to replace these vectors right here, or that vector rather, with its two components to simplify this. Okay, so you definitely want to do that. Any vectors that are not parallel with x or y in this type of problem, the first thing you want to do is simplify it. Okay, so I can replace that with his horizontal and his vertical component. And they both truly happen to be the exact same number. So we got this guy now. This is 70.71. And this is 70.71. Okay, so that's step one in the process. So now step two says to sum your vectors. So we're going to create that little chart like we did before. If you want, you can assign these numbers. That really helps, I think. But you got vector 1. This was vector 2. It has a horizontal and vertical, and this is vector 3. So I'm going to have 1, 2, 3 x vectors and my y vectors. Okay, I might want to move that y over a little bit. Okay, so for x1, it's negative 50. Going in a negative x direction, the y is 0. Okay, we all right? Okay, vector 2, your x is 70.71 positive, and the y is also 70.71 positive. Okay, for vector 3, your x is 0 and your y is negative 200. So we're going to just sum those. Let's see what we come up with. You guys can check my answers. So I'm getting a positive 20.71. So that's the direction of the x vector. And then we get 70.71 minus 200. So this gives me a negative 129.29. Okay, so this is giving me the x and the y components of the vector that's coming down through here. So we're going to come over here, and like I've told you before, you want to draw a picture of what's going on here so you can resolve everything. Otherwise, it's going to be hard to do. Okay, so I'm going to why is that not? Okay, so what is this telling me? It tells me that we are going, let me get my little tool here. It tells me that I'm traveling, oops. Oh, gotta move that thing. So it tells me that I'm traveling down basically, or that vector is going down at 129. So what this tells me is that the x component is 20.71, whoops, 20.71 this guy is 129.29, and the resultant here is like that direction. So you could get rid of all of these vectors and replace that vector with a vector that's coming down through this bracket at that magnitude in that direction. So to solve R, we use the Pythagorean theorem. See if I can do that up here. We've got 27(1) squared plus 129.29 squared, and we're going to take the square root of that mess. Okay, let's see what we come up with. I get a resultant value. You guys can check there. Let me know. I get 130.9 essentially, and this would be, if the base unit was pounds, this is pounds, okay? So those vectors, vector 1, vector 2, vector 3, can be replaced with one unique vector that is 130.9 pounds. So we need to know the angle. The angle here would be this angle theta, okay? So we know that theta, if we look at this as the arctangent of the 129 over the 20, so we got arctangent of opposite over adjacent, and that gives us I get a negative 80.9 essentially degrees. Okay. Is everybody okay with that?
Yeah.
So that's no different than component methods at this point. But we still have to know, now that we know that this thing is, 130 pounds and it's 80 degrees with respect to the x, we need to know where is that thing, because it could be here, it could be here, it could be anywhere along that thing. So what we're going to do is now utilize a moment. And if the moment of the original system is a certain value, the moment of this vector at that direction has to be another value, the same value, okay? So I'm going to take a moment about point A and solve the moment, and I'm going to define clockwise moments as positive, okay? Clockwise moments as positive. So if we start out with vector 2, what happens with vector 2 with the two components? Anybody tell me? Because I'm taking a moment here and the lines of action are coming right through, what's happening there? These guys are not creating any moment, okay? Because there's zero distance here and there's zero distance here. So if I look at this guy, he's 3 feet, perpendicularly measured to the 50 pounds, and if I'm putting that rotation there, it's tending to turn that clockwise. So we're going to have a positive rotation of 50 times 3. Okay. If we look at this, then this distance is 4 over to vector 3, which is 200 pounds. That's also a positive rotation. So I'm going to get a positive rotation, 200 pounds times 4 feet. Okay. So the vectors that are currently on that thing are inducing a moment of that about point A. We have 50 times 3 plus 200 times 4. And that gives me a moment of, it looks like 950 950, and this would be feet pound or foot pound. And it's a positive or a clockwise moment. Does everybody see how I got that? Anybody not understand what I did here? Again, if you look up here, because I took moment today, these guys drop out. Can anybody tell me how that would change if I would take moments down here? What would happen if I took moments at the corner of the bracket? Anybody see that? What would happen if I took moments here is the 50 is going to drop out and this one's going to drop out, and I'd be using these two to solve my moment. Okay. So depending on where you take moments, if you're selective, you can get rid of a lot of stuff. Okay. All right. So now we're going to use transmissibility, and I'm going to show you. I'm going to get rid of these vectors. So give me a sec. I'm going to erase everything up here because we don't need these vectors any longer. So I don't have this vector to contend with. And these vectors are gone. Not as easy on the as it is on the blackboard or whiteboard. Sometimes I can do it a little bit faster that way. Okay, so now comes kind of the hard part. So we know that this vector is 130.9 pounds, and we know its direction. So if I drew that vector, I can tell you that that vector is somewhere. It's somewhere over here. It's doing something like this. I just don't know exactly where. This is my resultant. I don't know where that is with respect to the corner of that bracket. Okay. So what I have to solve, and this distance is not 4. I'm going to get rid of that distance so you don't think that distance has anything to do with it. That distance has nothing to do with it. So this thing could be slid anywhere from here over to here. But one thing to think about, it would be impossible to have that vector over on this side of A because that would give me a negative moment, okay? So this vector has to be somewhere to the right of A because this is a positive moment. And this vector is going to have to induce 950 feet-pounds. So we're back into that same problem. We have to solve this perpendicular distance here, okay? And that's almost impossible. We don't know that. But this is where you can use transmissibility, and this is a little tricky. Let me draw something here. All right. This vector is composed of two vectors. A vector going down and a vector, let me do something here real quick. So I have a horizontal vector and a vertical vector. So that horizontal vector is the 20.71, and this one is 129.29. Okay, so this is where it gets a little tricky, but because this is my line of action, I can slide these guys anywhere I want. So I could slide these guys up this way, or I could slide it down here. Now, if I slide them down to here, or actually, let's do this. I'm going to slide it down to point A. By sliding those vectors coincident with point A, like here, okay, what's going to happen? Let me get these out of here. I'm going to slide this guy down and that guy down. By sliding these down, this one is now running through point A, so he drops out of the equation. So the only thing I'm left with now is this one. So what I can say now is this, that this distance from point A over, we're going to call that distance x. That force times that distance x has to equal this moment. Okay, so I can say that 129.29x has to equal 950. So x then is going to be equal to 950 divided by 129.29. And it tells me that that has to be 7.35 feet. So this distance here would have to be 7.35 feet. So I know now the resultant's magnitude, the angle, and the location. So you know this, you know this, and you know this. This right here is the tricky part. Okay, did I lose everybody? Did everybody see that kind of? Any questions? Max, you good?
I'm good.
Okay. Michael? Mitch?
It's just going to take a little bit to get used to.
It's gonna take a little bit, all right? There's
Confused.
about 3 problems on chapter 2 that I want you to work on towards the end. I think it's 19 and 20 and 22. Those are non-concurrent problems. So here's the thing. If you don't get it now, we will get it when we work through it on Thursday, okay? So you could probably do 80% of non-concurrence. You should be able to solve, you probably should be able to solve the resultant and its direction pretty easily. When you get to this point where you're using transmissibility and sliding, that's a little trickier, okay? So do what you can, and we will resolve the rest of this stuff then on Thursday, okay? So let me go back. I believe that's all we wanted to get into today. Yes, okay? So that's it for today's lecture. Now, so Thursday, we'll plan on meeting at 8 o'clock, run 52. Those problems that I want you to do, they're on your syllabus. They're also on Blackboard, the ones that I want you to do, finish out of chapter 2. And we'll do some problems, and we will probably start that deck project also, okay? So try to make sure that you're there for Thursday's class, because we're gonna cover a lot of these questions, I would imagine. Okay?
All right.
Anybody else question?
All good on this end.
Okay, perfect. Just give it a try, okay? It may, like I said, some of you might get, some of these problems are gonna get a little tough, but you're gonna have concurrence, non-concurrence, and parallels to do in the rest of the chapter. And we'll work those out, and I will go ahead and end the recording now and end the session. and I will get this, I have to get this thing formatted, so it takes a while, but I'll put the lecture back up on Blackboard for you so you can check it out on YouTube, okay?
All right.
All right, great. I will see you guys then on Thursday.